Imagine your tech lead comes over to your desk.
Okay, I'm picturing it.
And they hand you this spec for a massive, complex enterprise application. Like, we are talking 10,000 lines of code minimum.
Oh man, sounds like a nightmare already.
Right. But here's the catch. You have to write it strictly sequentially, starting at line 1 and typing all the way down to line 10,000.
Wait, like without stopping?
Without stopping, and you are literally never allowed to hit the backspace key.
Oh, wow.
Yeah. You cannot scroll up to edit a previous function. You can't, refactor a class. And you are strictly forbidden from running a linter or a compiler or even a basic syntax check until you type the very last semicolon.
I mean, just hearing that gives me sheer paralyzing panic.
Exactly. But that feeling, that is essentially the mechanical reality of how a standard large language model writes code.
It really is, yeah.
So, welcome to the late night shift. You're tuning in because you want to upgrade your mental models, and tonight we are digging through a huge stack of recent AI research papers.
Some really fascinating architectural teardowns in there.
Oh, totally. We've got developer documentation from leading framework builders, research from the big labs, and our mission for this deep dive is to understand the core bottleneck affecting, well, pretty much every software engineer trying to integrate AI into their workflows right now.
And that bottleneck is planning.
Planning, exactly.
All right.
We're exploring why these incredibly powerful models fundamentally struggle with looking ahead and exactly how the tech world is attempting to engineer a fix.
Because the architecture we rely on today it's created this massive disparity in capabilities, right?
Oh, for sure.
We have models that can synthesize dense documentation and they converse like senior engineers. But the moment you ask them to autonomously execute a multi-step, complex software deployment,
The wheels just fall off.
the entire system fractures. And if you examine the underlying mechanics of how tokens are generated, those fractures happen in highly predictable ways. We are looking at a mechanical limitation that requires borrowing, like decades-old classical computer science concepts to solve.
Right. But before we can look at the classical search algorithms coming to the rescue, we kind of have to isolate the trap these models are caught in, right?
Definitely.
In the developer community, we often refer to it as the left-to-right trap, which comes directly from the fact that these are autoregressive models.
Autoregressive generation is, it's the mathematical heart of the problem here.
Break that down a bit for us.
So when a model generates text or code, which it just processes purely as sequential tokens, right? It is moving strictly left to right. It calculates a probability distribution over its entire vocabulary and just selects the next token based entirely on the context window of tokens that came before it.
Right, the stuff it's already written.
Exactly. It possesses absolutely no inherent mathematical mechanism to look ahead. None.
Wait, really? None at all.
None. When the model generates, say, token number 50, it locks in a structural decision without any forward simulation of the downstream consequences that decision will force at, like, token number 500.
Oh, wow. So it's like
It is
bizarre.
continuously building a bridge while walking on it, completely blind to the opposite side of the canyon.
Okay, let me push back on that a little bit.
Sure, go ahead.
Because I think a lot of developers working with modern APIs might find that hard to square with what they see in their terminals every day.
I get that, yeah.
If it is purely predicting the next token without foresight, how does it successfully build novel integrations? Like, I can ask a model to write a script that pulls data from a highly obscure internal CRM API, right? And then I tell it to transform that data using pandas and push it to a completely different, unrelated charting library.
And it does it.
It does it. It will often structure that code perfectly.
Yeah.
Imports at the top, helper functions in the middle, execution logic at the bottom.
Yeah, it looks flawless.
Right, and it hasn't seen those two specific obscure APIs combined in its training data. So if it's not looking ahead and it's not drafting some internal architecture document before it starts typing, how is it succeeding at zero-shot reasoning like that?
Well, so the model creates a highly convincing illusion of foresight.
An illusion.
Yeah, through the geometry of its latent space.
Yeah.
We naturally anthropomorphize its output, you know. We assume it arrived at the solution the same way a human engineer would.
Right, by drafting a mental blueprint first.
Exactly. But in reality, the model relies on high-dimensional pattern interpolation. I mean, think about it. It has ingested billions of lines of Python.
Sure.
It understands the statistical shape and the required boilerplate of an ATI integration script. It understands the semantic relationship between data ingestion and data visualization.
So it's just following the grooves of what it's already seen.
Precisely. When you ask it to combine two obscure libraries, it isn't simulating the execution of the code. It is mapping the concepts to overlapping regions in its latent space.
Nice.
It knows statistically that after a certain prompt, an import token is just highly required, right?
Yeah.
Followed by configuration variables.
Right.
When the problem aligns with these deep statistical grooves, its left-to-right prediction mimics human planning almost flawlessly.
But when you push it off those statistical grooves, the illusion breaks.
Big time. The moment you introduce a truly novel logic puzzle or a system architecture with completely unique contradictory constraints that require forward simulation,
The left-to-right trap snapshot.
it's snapshot. The model will confidently code itself into a corner because the mathematical objective was simply to maximize the probability of the next token.
Not to globally optimize the final 10,000th token.
Exactly. And it cannot hit backspace when it realizes, oh wait, my variable scope is completely incorrect here.
Because autoregressive generation is a strict one-way street,
Yep.
which means simply scaling up the parameter count or training on more data won't magically invent a look-ahead mechanism.
No, it won't.
And that is why the research papers in our stack all point in a completely different direction. They are looking backward at classical algorithms. We're talking about integrating tree search into language generation.
And this represents a fundamental paradigm shift. I mean, researchers are adapting algorithms like tree of thoughts and Monte Carlo tree search.
Which are concepts that have historically powered stuff like chess engines, right?
Yeah.
And AlphaGo.
Exactly. And they are forcefully bolting them onto modern neural networks. The goal here is to transition the model from a system that blindly completes text sequences into a system that actively navigates logic puzzles.
Okay, to map this to something familiar for the listeners, let's look at pathfinding.
Oh, great analogy.
Yeah, so if I am building a simple video game and I have an NPC that needs to reach the player, a standard LLM acts like an algorithm executing a purely greedy search.
Right, taking the obvious next step.
Yeah. The NPC looks at the terrain, takes the immediate step that puts it closest to the player, and repeats. The problem is, if there is a U-shaped wall between the NPC and the player...
Oh, I hate when that happens.
Right. The greedy search just walks the NPC directly into the bottom of the U and gets stuck forever. It can't zoom out.
Because it only knows forward.
Exactly.
Hmm.
But tree of thought is like a proper pathfinding algorithm, like A-star or Dijkstra's. It simulates branching futures.
Mm-hmm.
The algorithm explores a path, realizes 5 steps down the line that the path terminates in a wall, and then it backtracks to a previous node in the decision tree to explore a different route.
And moving from that greedy token prediction to a simulated pathfinding approach fundamentally alters how the context window is utilized.
How so?
Well, with Tree of Thoughts, instead of generating one continuous, unalterable stream of code, the system forces the LLM to generate multiple possible intermediate reasoning steps.
Oh, I see. So these steps become the branches of our search tree.
Exactly. But the critical engineering challenge here is how you evaluate those branches. Like in a chess engine, it is easy to score a board state because the rules are mathematically rigid.
Right? Checkmate is checkmate.
But in software engineering and natural language, the rules are fluid. So developers are using the LLM itself as the value function.
Wait, it scores its own branches.
Yeah. The system generates, say, 3 possible ways to structure a database schema. It then prompts the LLM to critique and score its own proposals based on efficiency and scalability.
Oh, wow.
The system abandons the lower scoring branches, selects the highest scoring branch, and expands the tree from there.
It sounds like we are finally giving the model a backspace key, mathematically speaking.
We are. And Monte Carlo Tree Search, or MCTS, pushes this even further.
Let's get into MCTS.
So MCTS relies on 4 distinct phases: selection, expansion, simulation, and backpropagation.
It sounds intense.
It's powerful. When adapted for language agents, the system selects a promising node, expands it by generating new code snippets, and then simulates the future.
Simulates how?
Often by virtually, rolling out the rest of the script to see if it mathematically holds together.
And if it doesn't?
If the rollout fails, that failure signal is backpropagated up the tree, updating the value of the previous nodes. The LLM is no longer trapped making localized, short-sighted decisions.
It is slowly identifying the globally optimal path.
Exactly.
But, running MCTS inside a sterile, isolated lab environment to solve logic puzzles is one thing. Developers need tools that operate in the messy, unpredictable real world.
That is the big jump.
Right. We don't just want an LLM that thinks, we want an agent that executes. And looking at the architectural teardowns of modern agent frameworks, There are 3 mandatory pillars required to translate this tree search capability into real-world action.
Yep, the big three.
Task decomposition, constraint satisfaction, and replanning.
And these 3 pillars are the defining characteristics of an agentic wrapper. I mean, you cannot deploy an LLM into a production environment without an engineering framework that enforces these behaviors.
Let's look at the first pillar, task decomposition.
Okay, so an LLM cannot digest a prompt like, migrate our legacy user database to a new serverless architecture in a single pass.
Obviously not.
Right, the search tree would be infinitely wide, and the context window would overflow almost immediately.
So what does the wrapper do?
The wrapper must force the model to break the high-level objective into discrete, actionable subgoals. First, audit the current schema. Second, write the extraction script. Third, provision the new cloud resources.
And that brings us directly into the second pillar, constraint satisfaction, which is honestly the daily reality of software engineering.
Oh, it's everything.
We are constantly navigating strict boundaries, cloud budget limits, strict API rate limits, legacy code dependencies that we are not allowed to touch.
Yep.
But if the core LLM is inherently just a probabilistic text engine that wants to output the most statistically likely code, how does the agent framework actually force it to respect an API rate limit?
I mean, the model itself doesn't inherently care if it triggers a 429 error.
No, the model doesn't care at all. But the execution environment does.
Oh.
This is where the separation between the brain and the hands becomes critical.
Explain that. So the LLM generates a structured output, usually a JSON payload containing the exact tool it wants to use and the arguments it wants to pass.
Okay.
But the LLM does not execute the code. The agentic wrapper, which is usually a Python runtime environment, parses that JSON, executes the API call, and monitors the constraints.
Oh, so if the LLM's generated script tries to pull 1,000,000 rows at once and hits a memory limit, the Python wrapper intercepts that failure.
Exactly. The constraint is enforced externally, not internally, by the neural network.
Which acts as the perfect trigger for the third pillar.
Replanning.
Right. When a constraint is violated, the wrapper catches the exception, and that failure event forces the system to initiate replanning.
And replanning is where the system either achieves autonomy or collapses entirely.
High stakes?
Very. When the external wrapper catches that memory error or API rate limit, it cannot just freeze. It takes the standard error output, the stack trace or the HTTP response code, and appends it directly back into the LLM's context window.
So this is the equivalent of backtracking in our search tree.
Precisely. The system prompts the model, something like, you attempted this extraction method. It resulted in a memory overflow exception. Acknowledge this constraint and generate an alternative approach.
Wow. So the model reads the error, realizes its current branch is dead, and ideally pivots to a new strategy.
Right, like implementing pagination or batch processing.
You know, the combination of search trees, task decomposition, external constraint monitoring, and dynamic replanning. I mean, it makes it sound like we have completely solved AI software engineering.
It sounds great on paper.
But the developer documentation tells a totally different story. The gap between a human engineer's planning capabilities and an LLM's planning capabilities remains massive.
The gap is profound, particularly when the system is confronted with tasks that require flexible hierarchical reasoning.
Let's focus on that flexibility, because as developers, we are constantly zooming in and out of extraction layers.
Oh, all day long.
Right. If I'm tracking down a bizarre bug, I might be hyper-focused on the syntax of a single regex function.
Deep in the weeds.
Deep in the weeds. But then I realize the regex is failing because the data coming from the database is malformed, which means a completely different service is passing bad data.
Yep.
Which means our high-level architecture has a race condition. I can instantly snap from low-level syntax debugging to high-level architectural system design.
And cognitive scientists describe this as the human capacity to hold multiple levels of abstraction and working memory simultaneously.
We just do it naturally.
We fluidly shift cognitive resources between the micro-execution details and the macro-level constraints. But transformers, the architecture underlying LLMs, struggle immensely with this.
Why is that?
Well, the attention mechanism tends to heavily weight recent tokens.
Oh, right.
So as the model gets deep into the weeds of writing a specific recursive function, the initial high-level architectural constraints, which are located thousands of tokens back in the context window, they just begin to wash out.
It loses the plot.
Completely. It will write functionally perfect code that completely violates the broader system requirements. Or, conversely, it will get stuck in an endless loop of generating high-level pseudocode without ever committing to actionable execution steps.
Because neural networks natively struggle with that context switching, the current industry consensus is completely focused on hybrid architectures.
Hybrid is the word right now.
We are no longer trying to force the LLM to do everything. We are building systems that combine the flexible, highly associative reasoning of large language models with the mathematically verifiable, rigid reliability of classical algorithms.
It's the best of both worlds.
Right. To visualize this, imagine an engineering team consisting of two very different developers.
Okay.
The LLM is your wildly creative brainstormer. It can instantly generate 100 different ways to architect a microservice.
Some of them brilliant.
Some brilliant, leveraging obscure libraries in clever ways, while others are complete hallucinations that literally defy the laws of physics. The classical algorithm, the external solver, or the MCTS framework is your strict, clipboard-carrying project manager.
I know the type.
The PM doesn't invent the ideas. The PM's only job is to take the brainstormer's ideas and ruthlessly validate them against the constraints. Does this compile? Does this pass the test suite? Does this violate our memory limits?
And it makes sense because humans internalize this exact duality.
We do.
Yeah, we utilize fluid, intuitive System 1 thinking when brainstorming and rigid analytical System 2 thinking when writing unit tests.
System 1 and System 2.
Right. Because we haven't figured out how to make neural networks natively perform both types of reasoning reliably, we're engineering the duality from the outside in.
We separate the generative brainstormer and the validating project manager into distinct modules.
And force them to interact within a closed loop.
So for the engineers listening, building these hybrid architectures is the current frontier. We're bolting pathfinding algorithms onto autoregressive text generators. We are building robust execution wrappers to catch exceptions and force replanning.
That's the playbook.
But there is one final piece of this puzzle.
A crucial one.
All of this infrastructure, the search trees, the external wrappers, the project managers, is entirely useless if the core model lacks the ability to analyze its own failures.
The system requires self-reflection.
Right.
When the Python wrapper feeds a stack trace back into the context window, the model cannot simply guess a different syntax blindly.
It can't just try random things.
No, it must be capable of diagnosing the root cause of the error. If MCTS relies on the LLM to score its own branches, the LLM must be an accurate judge.
Makes sense.
Without a high capacity for self-reflection, the replanning loop breaks down into random trial and error. The model just throws spaghetti at the wall.
But with robust self-reflection.
With robust self-reflection, it analyzes the viscosity of the spaghetti, measures the texture of the wall, and mathematically adjusts its trajectory for the next attempt.
I love that analogy. And that exact mechanism, how we train models to evaluate their own outputs and act as their own critics, is going to be the central focus of our next deep dive.
It's a huge topic.
It really is. So as you build out your internal tools and agentic wrappers, keep in mind that your planning phase will only ever be as robust as the reflection phase that evaluates it.
Absolutely.
We've covered the mechanical reality of the left-to-right trap, the classical algorithms allowing AI to backtrack, and the external wrappers required to enforce constraints. But before we sign off, I want to leave you with a lingering thought.
Something for the late night shift to ponder.
Exactly. Something to analyze while your next container build is running.
Let's hear it.
If the absolute peak of modern AI engineering involves taking the massive, alien, highly probabilistic creativity of a large language model and heavily restricting it under the strict, rigid governance of classical search algorithms from the 1980s,
Right.
Are we actually building smarter, more capable reasoning engines? Or are we just artificially limiting a fundamentally alien intelligence to a human-readable format because a rigid search tree is the only way we know how to control it?
It's a profound question. When we force the model to show its work in discrete, logical steps that a human project manager can parse, we might be solving the alignment and control problem.
But at what cost?
We could be severely capping the ceiling of what high-dimensional latent space reasoning can actually achieve. Are we dieting the intelligence or simply placing a governor on the engine?
Keep experimenting with your code. Keep pushing the boundaries of your agent architectures, and we will catch you on the next deep dive. Stay curious.